All right, hi folks. Welcome to the Prince William Sound Natural History Symposium being sponsored by the Prince William Sound Stewardship Foundation today. I'm Betsy Oliver. I am not a part of the Stewardship Foundation, but I am helping out with today's event. And I will say that this whole thing is volunteer run, and the foundation runs on donations. And so we'd love it if you guys would take some time to head on over to their website and maybe make even a small donation. Every bit counts. I just got a text saying that we've already gotten $300 today. So thank you for that. We're excited. I'm here right now because Paul is having some technical difficulties. Something went wrong with his audio. So I'm going to do my best to fill his shoes. We have a couple of speakers coming up who are going to share about the Berry Arm landslide. And because I wasn't expecting to do this, that means that I don't have their bios in front of me, but we have Brent Higman coming up first. And so I'm going to invite him on screen, and he will just have to introduce himself. So bringing up Hig, as he's called, you may have met him before. All right. Hey, welcome back. Glad to see you. And sorry I don't have your bio. You're just going to have to introduce yourself.
That's fine. Well, I probably won't do much of an introduction, but that's okay. We've got limited time. We'll get to the interesting stuff. Should I just launch right in?
Go, take it away.
All right. So yeah, I'm going to, let's see. All right. Hopefully everyone's seeing my presentation now. I'm going to talk a bit about Berry Arm. I'll give just a really quick bit of background. Some of this might be stuff that you're familiar with already or not. And then the bulk of my presentation will really be talking about sort of the physical sciences, how we understand the geology of the system and what's going on. But I want to start with that background to make sure we're all on the same page there. So Berry Arm, shown here, has several large unstable sections of slope above it. These two here, landslide A and B, are the sort of best studied and probably most worrisome ones, but there are actually some over in this area as well. This is some work I did just to estimate how large that main Berry Arm instability is. It's this thick mass of bedrock along the slope that has been sliding downhill over the last few years. And it's unusually large. So there have been a number of large landslides in Alaska that have produced tsunamis in the past. These three, you'll hear them come up later in the presentation too, but they're much smaller than Berry Arm, and that by about a factor of 10 when you look at energy or volume. And Berry Arm's pretty active in recent years. So this is a plot of the retreat of the glacier. And we see Berry Arm, the landslide, moving along with that retreat. And as the retreat is slowed here, so has the motion of the landslide. And this is a concern, especially because it could, if that landslide fails, it could produce a tsunami that might have impacts throughout Prince William Sound, but especially in Port Wells and the associated arms there. So I want to talk a little bit about the physical links that, so the physical sciences that lead to this sort of situation. I'll talk a little bit about the basic background, how we get to the situation where there's an unstable slope. And then I'll use, largely relying on examples that we know about, to talk a little bit about landslides, tsunamis, and the impacts of those tsunamis. So starting with the really big picture here, what's going on tectonically under Prince William Sound is that there is a subduction zone. I'm going to start my timer now. I was meaning to do that at the beginning. And so there's an oceanic plate sliding under Alaska. Now you notice that this diagram, which I grabbed off the internet, is the labels are all wrong here. But subduction zones are actually really consistent worldwide. We can just relabel this with some familiar places around here. And what we're really concerned with is this little kind of beige chunk right here, which is an accretionary wedge. It's basically material that's scraped off the oceanic plate as it goes down. And this would, in a sort of idealized diagram like this, you see this kind of gentle slope going up from very deep water up to mountaintops. If we actually look at Prince William Sound, it's much more complicated. A lot of that complication, some of it does have to do with the tectonics. So we can see all the glaciers, the white areas, of course, are the high mountains. And here's Prince William Sound in the middle. Pacific Plate is coming in here. But as much as anything, the complexity here reflects the glacial erosion, the erosion by glaciers throughout this area. And glaciers are really extraordinary forces of erosion. They're one of the best ways to erode rock on the planet, perhaps the best way to do it. If you look at a glacier, at the amount of water that's moving as a glacier, the same amount of water, which would be the amount that comes out on average of a glacial river at the mouth, if it was a river, would erode far less than a glacier. And of course, the glacier sits in the bottom of a valley like this, and so it's eroding the bottom and sides of the valley, but not eroding the peaks surrounding it. And so in time, it makes the slopes steeper along the side because it's cutting away at the bases of those slopes. At the same time, the glacier is very heavy and it's pushing out on the walls of the valley, and so it actually provides support to the mountain, and helps basically support it as it becomes steeper. We call that buttressing, and then critically, as a glacier retreats, then it removes that buttressing. So we call that process debuttressing. And so it's quite common to see, as you have a retreating glacier, that some sections of the slope will become so unstable that they will crack and they will start moving. You can see this in other places as well. I've been working a lot on Gruink Lake, for instance, where you can really go and see some of these big cracks in the mountain. There are sinkholes up at the top. It's important to know, thinking about this sort of thing, is while it's quite common for these instabilities to form, for cracks to form, for the mountain to actually move, it sometimes ends up that the mountain returns to a state of stability, that in time the mountain stops moving, and hundreds of years, thousands of years can pass without a major landslide. So that's what we would hope would be the outcome in a lot of cases. I also wanted to note that there are other processes going on in a lot of similar settings around Alaska, and also connected. I'm not going to really focus on the climate change aspect of this right now, but these are also ways that climate change is driving decrease in slope stability. So in addition to debuttressing, even our southern coastal mountains that are relatively warm and certainly have no permafrost down at the bottom actually do have permafrost up high. And so as that thaws, it weakens the mountains. And we're seeing extreme rain and snowmelt events, and more so with warming climate. And that also has a big impact on slope stability. So that's how you get an unstable slope. Sometimes an unstable slope fails. And so this is one example. It's the Lamplugh landslide. So kind of down on the left here, you can see this big dark stain crossing Lamplugh Glacier. This happened June 28, 2016. It's a really big landslide. That's about almost 6 miles that the landslide ran out across the glacier. And one of the things that I think intuitively people might miss the mark on landslides is you picture small landslides, often, especially if we're talking about bedrock landslides, you picture rocks falling off a slope and kind of piling up at the bottom. But as landslides get really large, bedrock landslides get really large, they get much more mobile, and they tend to spread long distances out across even very low angle or flat valleys below. And all the more so if they're incorporating water or ice into them as they go. So I'm going to just jump out of this for a moment. Whoops, I'm going to have to do that. There we go. And I'm going to show you some satellite images. So these are blurry on my end too. This is a 1973 satellite image. We didn't have quite the satellite technology we have today then. But the blurry curved line in the middle is Tyndall Glacier. And so I'm going to click forward. It's just 1 year per click. And as I go, you'll see that the glacier gets thinner. And then sometime in the mid-80s here, we'll start to see the front retreat. So here's the glacier front retreating back into this fjord that's opening up. And at this point in 1988, it reaches about the position it is today in 2021, although the glacier has thinned some since then. It hasn't really retreated. And so as we go forward in time, you can see the glacier advances and retreats a little bit. But I'm going to just replay those last few years because something happens off on the side. Now watch this area here, and you'll see that this slope starts moving downward. And so up through 1999, this section of the slope above what's now called Tan Fjord moved down by hundreds of feet. And then it stopped moving. So through the early 2000s, it moved very little. And then in 2013, we get to watch a little bit happen here. So if you watch as we go from 2013 to 2014, especially pay attention to this band right here, we see the kind of barren areas increase because there are small landslides happening, and it shifted out a little bit. Into the summer of 2015, this whole area here shifted. And then late in 2015, so we see it in the 2016 image, the whole slope failed, and it ran down into the fjord. And so this event, the Tan landslide in October of 2015, was like that other example I showed. So here's what the valley looks like before. It was a highly mobile landslide. So it failed here, went down, it went miles down the bottom of the fjord. And it was so mobile that it actually went down. So this is the slope with the landslide back here. It went into the fjord, and parts of the landslide went up the far side of the fjord and formed these weird hummocks on the far side. So this is actually part of the landslide mass on the opposite side of the fjord. And of course, when you have a big landslide like this go into the water, it can generate a wave, a tsunami. And if we look at this is a map of what was inundated by that tsunami. And these are the heights in meters along the edge that the tsunami reached. So right here was the high point at about 633 feet. If you're down here a few miles, this is about 200 feet. This one over here would be about 70 feet. So it had it reached way up the sides of the fjord and stripped the forest from those areas. Now, of course, it's obvious that if you drop a bunch of rock into the water, it's going to make a splash and you get a wave. But I wanted to point out a couple of details to the way this works, like how it is that a landslide produces a tsunami. One interesting detail is that landslides don't generate a large tsunami if they're traveling slower than the tsunami they're generating, so or the potential tsunami. So if you imagine a mass just creeping into the water, and the water can just adjust its position as it goes in, there's no really dramatic wave produced. You might produce a very subtle long period wave, but it doesn't produce a really big wave, and it doesn't actually have as much energy either. Another fact is that the amount of energy, so the amount of energy that can be in the tsunami, is limited by how deep the water is. So if you have really shallow water, you can't generate much of a tsunami. And these two things play against each other. So when it's deeper water, tsunami waves travel faster. The water is able to adapt more quickly to the landslide. And so you actually, this thing can come into play, this factor can come into play with really deep water. This factor, it comes into play with really shallow water. And so there's kind of a middle ground where tsunami waves tend to be the largest given the speed that landslides typically travel, which is 50 miles an hour, 100 miles an hour, something like that. And so I'm listed a couple examples, 100 to 300 feet deep here. And this happens to be depths that are fairly typical for fjord bottoms. So that is part of why this setting is one where large tsunamis can happen. Now, after this landslide in Tan Fjord, I was involved in the post-tsunami survey. These are just a few photos from that. This is a boulder that was moved. I was studying somewhat the deposits, the sedimentary deposits, like these boulders and cobbles left by the tsunami. Even 10 miles away from the landslide, there was significant impacts, forest flattened, boulders moved. You could look in detail at wood that was sitting there that remained rooted at the material, the rocks embedded in it, to get some sense of how violent the flow was. And so we're, in this sort of survey, we're looking at the after effects. We're looking at the traces, the evidence of what had happened, but we don't have a direct observation. I drew this sort of cartoon of showing some of the processes that I thought might be contributing to what I was seeing. But this is speculative at the level of, hey, we've got these traces. How can we explain them? There are
we've got about 3 or 4 more minutes, and then we're going to get Dave on.
Yep. There are only a couple examples where we do have direct observations of tsunamis, and I just wanted to go through those really quickly. And so one is the Lituya Bay of landslide generated tsunamis, Lituya Bay tsunami in 1958. So this slope here failed and produced a tsunami that stripped the forest all along here, and so that's the barren areas that you see here. And there were 3 vessels in the bay at the time that experienced the tsunami, and we have some of their observations to know what happened. And one of the vessels, the Edri, they actually saw the wave coming, and they radioed the other 2 vessels, and then they tried to pull their anchor. Their anchor mechanism didn't work, so they instead dropped it to the limit of the chain of the rope they had on the anchor, and they moved out into the wave. The Sunmore attempted to flee out the mouth of the bay. Badger's anchor got stuck, and so they were still sitting there when the tsunami arrived. The Edri that was moving into the wave, the wave passed underneath them without breaking, and then broke behind them, swept them on shore, but they had a lot of water between them and the breaking front. It then swept them back out, and the vessel was unharmed. The Badger was swept across the spit. It's sort of miraculous that they survived, but it was a very close call. The Sunmore was lost as they went out into the mouth of the bay. And this was likely because, or a plausible explanation anyway, we don't really know what happened, but a plausible explanation for why this vessel was destroyed is because they moved into such shallow water. And that's right where the tsunami breaks and is most violent. One other observation we have is from Greenland a few years ago in Karat Fjord at the town of Nugatsiak. And there's this video is, I think, particularly valuable and shows a couple of people trying to rescue their boats as after the first tsunami wave arrives and before the second, which turned out to be a larger tsunami wave, came. And they eventually flee here. The videographer actually stays filming all the way to this point. And then at the last second, they turn and run. They are actually overtaken by the wave, but then you see at the end of the video that they flee out of it. And so we can use those sorts of observations to try to understand what the modeled tsunami, what the actual tsunami would be like in Port Wells based on these model results. We could say that the areas where the darkest colors are here, this might be the sorts of a wave that was seen by some of the vessels in Lituya Bay. At Nugatsiak in Greenland, the tsunami was about 9 meters tall, so that would be similar to some of the shorelines along here, where the wave is relatively small, but you're still in the fairly exposed area. And I think one thing that's interesting, you can actually pick out the way the wave gets taller right along the shore as it shoals up and goes into the water. You can also see the high wave heights at the heads of the bays, where you typically get this process that leads to kind of doubling the wave height as it reaches the ends of the fjords. And I know I don't have any more time here, so I'll go ahead and stop there. And I'd be happy to take any questions, or I don't know if we're waiting till the end for that.
Thank you. We're bringing, it sounds like Paul's back on. Oh, there he is. Paul is here. We did, I'll turn it over to him, but I'll say to everyone, we realized as we were looking at our schedule that we had not given this topic as much time as was merited. So thank you for putting in so much fascinating information so quickly. Paul, I'll turn it over to you, and I'm bringing Dave up on the screen as well.
But that's it. Sorry about this end. But yeah, we'll have Dave go, and then we'll do a Q&A at the end. Yeah. So.
All right. And hopefully my screen is coming across. There we go. Cool. Well, thank you, everybody. Again, I'm Dave Snider with the National Tsunami Warning Center. I'm the Tsunami Warning Coordinator here, and I'll be representing the federal and the state side of the monitoring and warning solution response for the Barrier Arm landslide risk. Since we didn't get to do introductions, I'll briefly say that Hig and his group with the academic side were the ones that kind of identified the risk and really brought this to the public attention there. and kind of lit the fire for everyone else to be a little bit more aware and be ready to respond to this. And so I'll be speaking from more of the monitoring and the warning solution side, where we're trying to get a better handle on what's going on and how we can advise the public and all of the thousands of people that use Prince William Sound for work, play, and for living around that part of Alaska here. The groups that have been involved with this, NOAA, USGS, the Coast Guard, U.S. Forest Service, State of Alaska, and the Alaska Earthquake Center have all been a part of the monitoring response here. And each one of these groups has had a part to play, whether it's the actual geology, the warning and safety, or the land use, or simply getting some seismometers and cameras up so that the rest of us could see what's going on in that part of the remote sections of Alaska. Here's some of the details, though. For geology and monitoring, the USGS Landslide Hazards Program has been doing some really critical work in monitoring the actual movement of the rocks on the slope. The Alaska Volcano Observatory put in some infrasound arrays in Whittier. So if you've seen some interesting equipment there in the last several months, that's probably what it is. The Alaska State Department of Geological and Geophysical Surveys has been doing a lot of LIDAR work. They're flying over with special sensors to actually examine the movement of the rocks in that way. And of course, working on bathymetry as well with the NOAA Coast Survey, and actually trying to understand how deep the water is there and if it can support a tsunami that would move with the quick enough speed that could damage and destroy some parts of Prince William Sound. And of course, the monitoring, the warning and response side, that's where the National Tsunami Warning Center comes in, working in combination with the state of Alaska, the U.S. Coast Guard, and of course, the local community emergency management groups. To remind you, the National Tsunami Warning Center has a general mandate to get our first alert message out within 5 minutes of detecting an event. The caveat to this is that is really set up to handle a seismic tsunami threat, so mostly earthquakes. We're not really set up to look at a landslide event and warn on that, and that makes this kind of system more of a moonshot for us. We're making it work. One thing we do know is that landslides and glacial fjords, especially within Prince William Sound, parts of Southeast and all the way down the western North American coastline, it's not a new threat. We know this. Nature does give us a warning, though. And we are able to listen to the natural signs and signals to get out of harm's way. And sometimes that's what it takes. Tsunami forecasts need time, though, for us to go through our normal process to warn on a seismic event. This is kind of the general flowchart of what we would do. At the first sign of a problem, a seismic event or an earthquake, we would issue an alert. And then we wait for a wave to reach a deep water sensor. A dart buoy is probably what you've heard of there. And then from that, we can start to work on our forecast. After that wave reaches the coastline, we can scale that forecast again and continue to adapt that toward the observations and provide better information to people who have not seen a wave just yet. And of course, all of that is improving confidence as we go with time. And that takes a lot of time to make that happen. The problem is with this Prince William Sound situation, and in Barry Arm specifically, we don't have a lot of time to do that. And we're talking about an order of minutes rather than hours to refine a forecast and get that to people that need to get out of harm's way. So we're designing a new system that is really focused on this Barry Arm problem, and it's entirely possible that as we go over the next several years or decades that we'll be looking at adapting and improving the system as we go. Right now, generally speaking, if a wave leaves Barry Arm, the initial water level change could reach Whittier in about 20 minutes, Chenega in about 30 minutes, Titlik in about 40 minutes, Valdez in about 45, and Cordova in about an hour. And that is just the initial wave. It's really important to understand that the initial first wave may not be the largest wave, and that strong currents and unusual currents could continue to damage areas and cause problems for several hours after that. Some of the National Tsunami Warning Center's initial modeling from last year shows a similar picture to what Hig was presenting a minute ago. Look at the red areas. Those are the north and western parts of Prince William Sound up around Point Duran, Pakenham, and Barry Arm North Shore. And if you notice those three gold stars, those are the three sensors that we put in several weeks ago. Very close to Barry Arm and just south of the landslide area. Whittier's on your left side of your screen, Valdez to Titlik, Cordova on the right side, and Chenega on the bottom left. The red areas are the limited amount of travel time there, so anywhere from 0 to about 20 minutes. You can see that around the Berry Arm, that's anywhere from about 0 to 10 minutes. Whittier is closer to 20. And then, of course, you get into the yellows and the oranges there. That's more on the course of 30 to 40 minutes. And then Cordova, again, is closer to about an hour out. But if we look at our sensors that we've installed there around Point Duran, that's just south of the landslide, we think that we will measure an initial tsunami wave there around 2 minutes time. Around the North Shore, about 4 minutes. And then around Point Pakenham, which is a pretty popular kayak spot, about 7 minutes or so. And then, of course, that's all set up to help alert Whittier as fast as possible, where that travel time could be anywhere from about 20 to 24 minutes. So what did we install? This is basically a pressure gauge. A transducer is underneath the water, rigged up to a cable that goes up to a drier spot above the highest tide line. And that electronic system relays at pressure change about every 2 seconds there. So we will be able to detect an unusual change very quickly. And as we see that cascade down the Berry Arm, which should give us a pretty good idea that some type of catastrophic change is coming down Berry Arm, at which point we would issue a warning. If you happen to be out in Prince William Sound and you come across a truck box with a tsunami symbol on it, please leave it alone. These are out there in the wild, and there's really not much to keep you from walking up on it there, but we try to do our best to tuck it away and make it not something that you're going to notice very easily. However, they're out there in the wild, and you'll see perhaps a yellow cable draped down the rock, down into the water, and below that is the pressure transducer there. And hopefully, most of the time, it will be underneath the water. If not, we're probably in an extremely low tide cycle there. But it's a simple design, something that's designed to handle the Alaska elements, and something that's been in use across many other parts of Alaska for many, many years, and something the folks here at the National Tsunami Warning Center came up to handle unique situations to help us do a better job of knowing when seismic waves were moving toward the coastline. So once again, we put in three gauges there in the Berry Arm region, and we expect that we're going to see that wave travel from north to south as a catastrophic wave were to move down through the Berry Arm in that situation. This is, of course, expecting that we're going to see something more than boat wakes, more than kayak wakes, something that would be a little bit more than just a few rocks dropping in the water. This would be something that would be a sizable change in that water level leaving Berry Arm. As I mentioned, glacial landslides or changes in the fjord there are not uncommon across Prince William Sound. And that's why it's really important to remember what the natural tsunami warning signs are. If you feel a long or strong earthquake, obviously that's a change, right? We usually say about 20 seconds or more, it's time to get away from the water and head up to higher ground. But if you're at the water and you see a sudden rise or fall of the ocean, or you hear a loud roar, which could be a landslide in this case, or some type of water noise from the water itself, let that be a sign to you that some unusual changes are taking place and you need to move to higher ground. All of that could mean a tsunami is coming, and that is your first, best, and probably your fastest signal to get away. If we issue an alert for Berry Arm, chances are it will be a tsunami warning. We're not going to try and forecast the event at this point. We're looking to issue you an alert that tells you to get away from the water and get to safe territory as quickly as possible. So that also means dangerous coastal flooding, powerful currents could be possible, and again, you need to take action immediately. Most of the time, the alerts that you see from the Tsunami Warning Center are more on the information statement level. And basically that means we've detected an earthquake. It's not likely that it will produce a tsunami, and you can relax. It's not a big deal. Our Tsunami Warning Center operation is set up to run 24/7 by 365. You can see Chris Popham there monitoring a quake a couple years ago in the center here in Palmer. We have a sister center that also backs us up at the Pacific Tsunami Warning Center. They're located in Honolulu, Hawaii. And between the two centers, the unique operation there is set up and designed to monitor for seismic tsunamis across the United States. And of course, we'll be adding the Berry Arm threat to that list. How can you get that information if something is happening in Whittier or any parts of Prince William Sound? If there is a detectable wave, the Tsunami Warning Center will issue a tsunami warning. You have ways to get that warning over a tsunami siren. If you're in any one of the communities in Prince William Sound, you'll hear that. And I believe Whittier is either about to or has already added a second siren. They're working on that and adding more coverage to more areas and parts of town. The NOAA Weather Radio and the Marine VHF are certainly ways that you'll get that information. The Coast Guard will be passing that on right away as well. So we're tied into the emergency alert system with the Coast Guard, and they'll pass that on just as quickly as possible. If you have a cell phone and you're in cell range, and many parts of the Port Wells area, as well as regions up toward Barry Arm, are in cell phone coverage, you can get a wireless emergency alert. A tsunami warning is part of that, and you'll get that very, very quickly, and it will take over your phone in a very annoying and loud way, but it does get your attention. That'll be a quick alert there. And of course, if you're in town watching radio, TV, or on the internet, a lot of things will take over your favorite websites and tell you something like that is happening. There's many other types of subscription services there. Some of those are governmental, some of those are public and paid for. But I encourage you to find at least 2 of them that you know that you can reliably depend upon. Try them out. Make sure that you've got a way to be familiar with those and use them, because trying to get signed up for something at the last minute just doesn't work. So what is your risk? If you are looking at a situation where it is simply a landslide event, we're talking about an issue that will affect mainly Prince William Sound, Whittier perhaps, and some of our Prince William Sound communities. In this case, I would expect a quick emergency response, so help to get out of harm's way, help to get out of trouble once the event has occurred. But if we have an earthquake that triggers a landslide, and we have a landslide event at the same time creating a tsunami, there's going to be a much slower emergency response. And why does that matter? Well, it could mean that Prince William Sound, parts of Whittier, or any of our other communities may not get the help they need for quite a long time if a significant earthquake has occurred. So if a significant wave does move into harbor, it's important for me to remind you that debris could interrupt normal operations and make rescue very difficult, if not impossible, for a long time. Moving to shore and disembarking would be your best option if you have time. And you heard the story that Hig was sharing about Tan Fjord. But it's also important to consider that every part in Prince William Sound is going to be different. Coastlines are different. Some are very hard to get off and disembark, and others you might be very close to a shore that you could get up and away to higher ground very quickly. So you're going to have to make the best choice about your situation, but it's important for you to be thinking about that no matter what part of Prince William Sound you're in. The other side of that is to expect dangerous and unusual currents for a long time after the initial change in water level or that tsunami wave. And that could mean there's a lot of debris in your way as well. That could make it hard for you to move. If you're in town, though, I think you have a much easier option, though it will be tricky to get to where you need to be as fast as you need to be. Think about your escape route for each point in your day. Practice plan to get from your location to a safe evacuation point in higher ground. If you're on the water, make sure you understand what your float plan is and where that's going to take you. Make sure you've got a float plan filed with the harbor master, and make sure that you practice a plan with your family and friends. Quick look at the Whittier inundation map here. The red area is bad. The orange area or yellow area is a little less bad. This is produced with work from the Alaska Earthquake Center and the folks at UAF, as well as the National Tsunami Hazard Mitigation Program. And the red areas are regions that could see water flooding or inundation above 6 feet. That includes all of the harbor. That includes the areas where the shops and the restaurants are, all the way down to the rail yard and the freight dock. You can see there is a cruise ship in town there, and that's all the cruise ship region, and that extends all the way up the main road toward the tunnel. A little bit in town above, I believe, the Whittier Road itself, it's about a 1 to 6 foot inundation line, or about 1.8 meters there. We're talking about water that could reach anywhere from 20 to 30 meters, depending on which model we're talking about. The good point to point out here is that the Baggage Towers area, which is the bottommost arrow, is above all of that. That is on the bottom part of your screen, and all of that is in drier land. So if you are a pedestrian, someone in a car, that would be the point that I would rally to, and do yourself another favor and just keep going up to the trailhead. Travel time is going to be a problem, though, because Whittier is a pedestrian town, especially when we have guests and visitors there. And this is the part that troubles me every time I look at this. Simply that down by the harbor, your travel time on foot across the rail yard and across the tracks or through the tunnel on, I believe it's the east side, could be anywhere from 10 to 20 minutes. And if you recall the travel time numbers that we were talking about, that could range anywhere from about 10 to 15 minutes to get out of harm's way once an initial warning message is sent. So with that, I would encourage folks to continue to stay up to date on the goings-on of the research, of any activity that we have developed by your federal, state agencies that are doing their level best to keep information coming your way. And the very best way I think you can do that is you can go to your favorite search engine and type in Berry Arm, Landslide, Tsunami, and you'll find this page at the top. It's the Department of Natural Resources, State of Alaska, Geological and Geophysical Surveys. And every 2 weeks right now on the schedule, we're publishing a status report and update. It has any new changes there. It has any new science that's being brought forward. You can also subscribe to this update to be sent to you, so you know when it is coming your way and it's been updated. And like I said, it's on about a 2-week cycle right now. But if changes are happening, if we're detecting some unusual movement or we've got some new science to share, that update cycle could be increased there to make sure that you're staying aware. I believe that is my last slide there. Yes, it is. So by all means, fire away questions there. And if you can't reach me here today, we're always happy to help and get you the information that you need so you can make a better and safe decision. Thank you.
All right, thanks. That was Dave Snider with the National Tsunami Warning Center and Brent Higman as a geologist living in Solovia. So a couple questions for you guys. Could an earthquake trigger the landslide? I bet the answer is yes.
Yep.
I mean, my story is last summer I was out and I heard a rumble off to the north, and I'm like, there it is. And it just was an earthquake, right? And then 2 days later was the Sandpoint event, Chinook Bay event that evacuated Kodiak and Homer. So I used to tell people it's not the tsunami that you think is going to get you; it's the one that you might not think. Another question we had was, I think we answered, was how that Berry Arm sensors work. They sound like pressure, correct?
That's right. They're pressure transducers, so that information is measured very routinely, and then that's sent back across the network, and we get that information about every 2 to 3 seconds, I think. So it should be a pretty continuous plot of data for us.
Yep. And if we're not from a sound community and are recreated on a boat in the sound, will we receive a cell phone alert? And I'll let you answer the alert part. I will say that not all the sound has cell phone coverage.
Right. That's the danger. Relying on cell phone coverage if you're in a place that you don't normally go or that isn't in that coverage area, you're not going to get the alert. You have to have a cell phone signal to get a wireless emergency alert. So I would look into a satellite communication device, and most of those systems have a subscription that will allow you to get those type of alerts.
And the last question we had is, if on board a boat would be moving to deeper water also be a reasonable step to take? I would assume that's very situational.
It is, and the deeper the water, the better off you're going to be. The thing to think about in Prince William Sound, and something I was thinking about when I was out there a few weeks ago, was that, you know, the places you want to be are next to the coast, right? You're fishing, you're doing your activities, you're exploring. You know, most of your transit time will be out in the middle of the water, but you're going to be closer to a coast for a lot of the other things. So if you can get away from the coast quickly into deep water, that would be an okay solution. But knowing where you are is probably the best idea. Knowing what your plan is for that particular point is a must.
Great.
I think it's particularly important for vessel operators who have passengers on board, where, you know, generally, I think, you know, they're really familiar with the area, and I think knowing that deep water provides a tremendous amount of protection. It is amazing how much less violent the wave is in deeper water, and so I think especially for vessel operators with passengers, that's one of the best options you have.
Thanks, guys. We are out of time. There's one more question I'm going to post in the chat, so if one or both of you want to look at that. For all the audience, we're going to move on to our next session, which is a concurrent session. One is Prince William Sound weather, and the other is a brief history of Whittier, Alaska. So you can go to the scheduled session and click on the one you would like to go to. So thanks, guys. Once again, Brent Higman, geologist out of Soldovia, and Dave Snider with the National Tsunami Warning Center. Thanks for joining us today.